Okay, so we'll start with that imagined level data series, some sort of flat line that's obscured by noise, and we want to average out the noise to find the underlying level and project that level into the future as a safe, sensible forecast. Well, this requires what's called single exponential smoothing. It's also called simple exponential smoothing because it's called single because there's something called double, where we do it twice. It's called simple because it deals with the most uncomplicated case, the level. And so we're just trying to estimate the level of the time series. Now here's where we come in with the math. We'll say x of t is the variable we want to forecast at time t. So we have a set of, say, sales observations or demand observations at time 1, time 2, time 3, times 4. That's a time series of data. And we'll say S of t is the smoothed data at time t. And remember, with exponential smoothing, we actually believe that S of t is a more sensible basis for making a forecast because x of t has the underlying level in it plus a whole bunch of noise which is just there to confound us and confuse us and lead us astray. So what we're going to do is, remember the picture. Here's x of t against t. It's zigzagging along. S of t, I'll try green here. S of t is going to be our estimate of where the middle is, and it'll form the basis for a forecast. So the key thing is, where is S at the final time, which we'll call capital T. So that's the picture. Now we need the equation for how we compute the smooth value, because we'll go through here and keep computing these, and at the final data point, that will be the launching pad for our forecast. That'll be the level we'll use to predict for the future. So the way this equation works is S of t, there are a couple of ways this can be computed, and I'll show you two. We could say it's a weighted sum of the current value and the previous idea of where the middle was. So we can say, let's say alpha is a parameter, which is also perhaps called a knob. It's something we adjust. It can go between 0 and 1, and we have to set that. And we'll talk about whether it should be closer to 0 or closer to 1. But we'll pick a number, say 0.1 is a common starting point. So we'll say the smooth is a function of the current data point and the previous idea of where the middle was, which is the smooth one time period before. And it's a weighted sum, so we give a weight like 0.1 to the most recent data and 1 minus 0.1, 0.9 to the oldest. So we get the new idea of the middle by having a 90-10 split on the weights between what we thought the middle was at the last observation and what the new news is coming in from the real world, x of t. And this gives us our smooth value. And then the forecast, which we'll call a forecast of x at t plus any forecast horizon, is just simply going to be where we think the smooth was at the very end of the time series. That's our current idea of where the middle of the action is, and everything else is going to be noise. So we'll use this final value as the forecast out as far as you can see. So this is one of the ways you can write the equation. You can see there's a multiplication. There's a multiplication and an addition. 1 minus alpha would be stored as a number, like 0.1 and 0.9. So 2 multiplies and an add for each time period is not a lot of math. It goes through very quickly. And you only have to, for each item, store what the value of alpha is. And it may change from item to item. But that's the essence of single exponential smoothing. There's another way you can write this. It provides a different sort of interpretation. We can say S of t is our previous idea of where the middle is, S at t minus 1, yesterday's value for the smooth, plus an adjustment factor, alpha, of the difference between today's value and what we expected it to be based on yesterday. So we could say we're adjusting our green curve, our smooth curve, by looking at the discrepancies between the data and what we thought the data would be. So if the data come in surprisingly high, this will be a positive number. We'll add some fraction of it. We won't overreact and go directly to replacing S with X. We make a little adjustment up if the newest data point was up. Or if the newest one were low, then this would be an adjustment down. So this is another way to think about the way exponential smoothing works. But in both cases, we're always doing a kind of combination of what we thought was happening, where the middle was, and then adjustments as new data come in. And that can be especially important if you're not in a simple world like this. A realistic world is that nothing stays flat forever. Things change, and there's what you might call drift in the level of the series. And exponential smoothing is designed to be able to float up or down with the drift, so it's always adjusting to what's happening now. So a more realistic picture of the data may not be this simple picture, but it may be something like this. We're doing this, and then all of a sudden we're here, and then maybe we're back to where we used to be. So we would call this a level series with drift. It's sort of level at one level, then it drifts to another level, and then it comes down again. And in this particular case, we want the adjustment to happen in the calculations. We want the exponential smoothing to be down here, and then to come up and be here, and then to react and come here, and finally this would be our forecast. So we have to think about how can we make it track these sorts of drifts. But if it does drift, this sort of adjustment formula allows us to drift with it and to take account of those changes. So we don't insist that the world is flat. The world can float, and this technique can float with it, and that's very useful.